Hello and welcome to this video about heterocyclic chemistry. Here we will look at some synthesis of pyridines. So, as we've seen in a previous video, a general strategy for heterocycle synthesis is the cyclization and dehydration of the heteroatom source, for example ammonia, and the backbone, which is typically a dicarbonyl species. So if we want to make a six-membered ring, we have 5 carbons in a row with a carbonyl on each end, like this 1,5-dicarbonyl. And if our nucleophilic ammonia source attacks each of the 2 carbonyls, it will lose water twice to give us the corresponding dihydropyridine. If that dihydropyridine has a leaving group, such as halide, then you can generate the aromatic ring directly, or we can oxidize the 1,4-dihydropyridine. One of the most iconic heterocyclic chemistry reactions is the Hantzsch pyridine synthesis. Now this approach takes simpler building blocks, specifically 1,3-dicarbonyl compounds, an aldehyde, and a source of ammonia. And these are combined to make a dihydropyridine. There are 3 steps to this. First of all, we have the aldol condensation between our 1,3-dicarbonyl and our aldehyde. So the 1,3-dicarbonyl can exist in an enol tautomer, and that tautomer is nucleophilic, so we can push the arrows through from the OH, through remaking the carbon-oxygen double bond and attacking from the carbon between the 2 carbonyls onto our aldehyde. Then, after the new carbon-carbon bond is complete, this is the aldol part of the reaction, the hydrogen between the 2 carbonyls is still acidic, so that can be tautomerized, and then we can push the arrows back through to lose OH2 and generate the unsaturated compound. So this is the condensation part. So we have aldol condensation between a 1,3-dicarbonyl and a aldehyde. The second part of this process is the formation of an enamine. We have a source of ammonia, so ammonia is a gas, so typically in the lab we will use something like ammonium acetate, which will have an equilibrium between the salt and free ammonia. The nucleophilic amine will attack our 1,3-dicarbonyl species. Notice this is the same 1,3-dicarbonyl species as before, and this is all happening at the same time. Then our lone pair pushes in to break the carbon-oxygen bond, and then we lose a proton to complete our enamine formation. In the final part of the synthesis, these 2 fragments come together. Our electron-rich enamine attacks via the carbon onto the Michael acceptor, so conjugate addition to our unsaturated aldol condensation product. Then tautomerization gives us back our dicarbonyl. And now we can do the cyclization to give us our 6-membered ring, so we can push the arrows through via the nitrogen to attack that carbonyl. And finally, we can get loss of water to give us the 1,4-dihydropyridine. You'll notice that the products here are symmetrical, and if you want to make an unsymmetrical product, then you'll need to do each of the 2 steps at the start separately. The product here is also a 1,4-dihydropyridine, so if you want the fully aromatic version, a separate oxidation is required. We can go through this more slowly. Our first step involves the keto-enol tautomerization of our dicarbonyl. The enol tautomer shows how it can be a very good nucleophile. We can push the arrows from our oxygen through via the carbon to attack our excellent electrophile in the form of an aldehyde. This is the aldol product. We turn an aldehyde into an alcohol. That's where the name aldol comes from. But because this molecule has still got acidic hydrogen, we can access that enol tautomer once again. Then push the arrows back through to eliminate water. And it's E1CB mechanism. And so this gives us the aldol condensation product. So an aldol reaction followed by the loss of water. And this is our key microacceptor. In the second step, which is happening at the same time as the first step, our 1,3-dicarbonyl species reacts this time with ammonia. Our nucleophilic nitrogen attacks the electrophilic carbonyl to make a new nitrogen-carbon bond. And then we get loss of water. So the lone pair comes in, breaks the carbon-oxygen bond, this forms an aluminium which can rearrange to quench the positive charge and form our enamine. So we have our aldol condensation product, which is a microacceptor and a good electrophile, and we have our enamine. The lone pair of that nitrogen makes the system electron rich, so it's a good nucleophile. So a good nucleophile reacts through the carbon onto our carbon of our microacceptor to make our new carbon-carbon bond. At this stage, we can tautomerize the enol to regain our carbonyl. And now we can lose an acidic proton between our imine and our carbonyl and push the electrons through that nitrogen to attack our electrophilic carbonyl. And this makes our 6-membered ring and the key nitrogen-carbon bond. Our final step is the loss of water, so our nitrogen lone pair can come in, break the carbon-oxygen bond, and then the resulting positive charge can be quenched by the loss of a proton. and that delivers our dihydropyridine product. Again, it's symmetrical because we use the same 1,3-dicarbonyl to make both sides, and we'd have to make those two starting materials, the enamine and the microacceptor, separately if we didn't want that. And if we wanted the pyridine, we'd have to oxidize this separately. So an alternative approach to synthesizing pyridines involves constructing the 6 members of the ring from 3 separate pi systems. And this is a transition metal catalyzed 2+2+2 synthesis. So 2 of our pyridine atoms will come from alkynes, and this reaction works best if the 2 alkynes are tethered together, because the 2 alkynes make a great ligand for rhodium catalyst. So the rhodium sits between our 2 pi systems, and then it can undergo an oxidative insertion reaction where we make a new bond between the rhodium and the carbon of one of the alkynes. This breaks the alkyne bond and makes a new carbon-carbon bond between the 2 alkynes, which breaks the second alkyne and makes a new carbon-rhodium bond. The resulting is a 5-membered heterocycle with a rhodium atom inside. And then we add in the second component to our mixture, our nitrile. And this behaves a little bit like a Grignard reagent. A Grignard reagent is a carbon bonded to a metal and will attack as a carbon nucleophile. Well, this is what happens here. Our rhodium carbon bond adds across the nitrile, so we end up with a new carbon-carbon bond and a new nitrogen-rhodium bond. This 7-membered ring will undergo reductive elimination, which will give us back our rhodium 1 catalyst and deliver the 6-membered pyridine product. If we look at this a little bit more slowly, the key interaction here is the pi bonds of our 2 alkynes, which are very good ligands to a rhodium 1 catalyst. So a rhodium 1 catalyst sits between the pi systems and undergoes oxidative insertion. So we can draw an arrow from the rhodium to the carbon. That breaks one of the pi bonds. We can draw an arrow from one alkyne to the other. That breaks the second pi system. Then we can draw a last arrow from the carbon back to the rhodium to give us our 5-membered heterocycle with a rhodium in. At this stage, our nitrile group also coordinates to our rhodium. And then the rhodium behaves a little bit like a Grignard. It adds across our pi system. So we get the carbon adding to the carbon end, and then the nitrogen adding to the rhodium. This results in a 7-membered system. 7-membered rings are always a little bit tricky to draw. And this 7-membered ring is turned into a 6-membered ring by reductive elimination of the rhodium. This gives us our pyridine as well as our rhodium 1 catalyst, which can go on and promote further reactions. In this video, we've seen 2 different pyridine syntheses. We've seen the classic Hantzsch pyridine synthesis, which is a multi-component reaction between a 1,3-dicarbonyl aldehyde and some kind of amine that gives us a symmetrical 1,4-dihydropyridine. And we've seen a transition metal 2+2+2 synthesis between alkenes and a nitrile. Thank you for watching. I'll see you next time.